The following lecture is the first in a series that covers the HNC Electrical Engineering Unit, FY 9E, DC and AC Principles. This lecture covers the basic concepts, definitions and relationships that underpin all electrical engineering theory. The subject elements to be covered in this lecture are listed on this slide. A summary of all the information covered, the worked examples, and a set of self-assessment questions are contained in the accompanying workbook. In engineering, we work with both very large and very small values, so we need to consider both the mathematical notation and the required precision of numeric quantities. Throughout this unit, we will be working with a precision of 3 significant figures. The following example is in the accompanying workbook, Numbers and Notation, Significant Figures. Round the following numbers to 3 significant figures. Taking the first number, we look at the first 3 digits, 9, 3, 4, and then look at the 4th digit. It's a 7. This is greater than 5, so we round up the 3rd digit, and the 4 becomes a 5. The rest of the numbers after the 3rd digit and to the left of the decimal point are replaced by zeros. With the second number, we look for the first non-zero number and then take the next 3 digits, 1, 7, 6. And then look at the 4th digit, it's a 4. This is less than 5, so we just leave the 3rd digit unchanged. There are no numbers to the left of the decimal point, so no zero infill is required. In the final number, we again look at the first 3 digits, 2, 4, 9, and then look at the 4th digit, it's a 5. So 5 or greater, we round up the 3rd digit, and the 9 becomes a 10, which ripples through to the next digit. Again, we infill the rest of the numbers to the left of the decimal point with zeros. Scientific notation is a useful technique to manage all the zeros present in very large and very small numbers. Here, all values are expressed as a number between 0 and 1, and then multiplied by 10 to some power, termed the exponent. The following example is in the accompanying workbook, Numbers and Notation, Scientific Notation. Convert the following numbers to scientific notation. Taking the first number, we need to move the decimal point 7 steps to the left. So the number becomes 0.935 times 10 to the power 7. With the second number, we need to move the decimal point 2 steps to the right. So the number becomes 0.176 times 10 to the power minus 2. Finally, on the third number, we move the decimal point 4 steps to the left. So the number becomes 0.250 times 10 to the power 4. The following example is in the accompanying workbook, Numbers and Notation, Engineering Prefixes. In engineering, there are certain preferred exponent values, and they are 10 to the power 6 mega, represented by the letter uppercase M, 10 to the power 3 kilo, represented by the letter lowercase k, 10 to the power minus 3 milli, represented by the letter lowercase m, and 10 to the power minus 6 micro, represented by the Greek letter mu. You are expected to recognize these prefixes and know the exponent power they represent. To convert a number to a standard exponent, you can use the ENG key on your calculator. Simply enter the number into your calculator and press ENG. Convert these numbers to use engineering prefixes. Taking the first number, 0.935 times 10 to the power 7, becomes 9.35 times 10 to the power 6, or 9.35 megohms. The second number, 0.176 times 10 to the power minus 2, becomes 1.76 times 10 to the power minus 3, or 1.76 milliamps. Finally, the last number, 0.250 times 10 to the power 4, becomes 2.50 times 10 to the power 3, or 2.50 kilovolts. In order to understand electricity, it is necessary to understand something about atoms. All matter is made up from atoms, which are built in turn from a number of subatomic particles, namely negatively charged electrons, positively charged protons, and neutrons. An atom is the smallest part of an element that still retains all the characteristics of the element. The Bohr model, developed in 1913, considers atoms to have a planetary-like structure consisting of a central nucleus containing the protons and neutrons, surrounded by orbiting electrons. Here is an example of a hydrogen atom. It has one proton, one neutron, and one electron. The proton and the neutron are contained in the central nucleus. The electron is in an orbit about the nucleus. To be charge neutral, an element must have the same number of electrons as protons. Each element has a unique number of electron-proton pairs that distinguishes it from all other elements. However, one element can have different numbers of neutrons, which are called isotopes. Where an atom has many electrons, they are constrained to be in certain fixed orbits, termed orbitals or shells. Here is an example of a sodium atom, which is a metal. A sodium atom has 11 protons, 12 neutrons, and 11 electrons. In the nucleus, we have the 11 protons and the 12 neutrons. And the electrons are arranged in shells about the nucleus as follows. 2 electrons can go in the first shell. 8 electrons can go in the second shell. Finally, 18 can go into the third shell. However, When we get to the third shell, we only have one electron left to be placed, so just one electron goes into the third shell. This situation characterizes metals. They all have only one or just a few electrons in their outer shell. In metals, the electrons in the outer shell, being somewhat shielded from the nucleus by the other complete shells, can gain enough energy to leave the atom, and because of this, they are termed free electrons. In some materials, the outer electrons can get enough energy to escape the atom, and these are termed free electrons. These materials effectively have a sea of randomly drifting electrons within their structure. The higher the temperature of the material, the more free electrons will be present and more active in their behavior. Electrical conductors are materials that can carry an electrical current and are made from elements that have a large number of free electrons, for instance, metals. Electrical insulators are materials made from elements that have none or very few free electrons and hence inhibit the flow of current. Charge is the name given to the unique electromagnetic property possessed by electrons and protons. It cannot be found anywhere else. The properties of electrons and protons are very similar but have some obvious differences. By definition, electrons are said to have a negative charge and protons a positive charge. The symbol associated with charge is the letter uppercase Q, and its unit is the coulomb, abbreviated to the letter uppercase C. As the amount of charge carried by one proton or one electron is very small, the unit of charge is always considered in multiples of electrons or protons. 1 coulomb of charge is the charge possessed by 6.25 times 10 to the power 18 electrons or protons. A charged subatomic particle possesses an electrical field similar in nature to the magnetic field around a magnet. As a result of this field, if two charged particles are brought together, a force will exist between them. This force is measured in volts. Particles with unlike charges, i.e., a positively charged atom and a negatively charged electron, will experience a force of attraction, while those particles with like charges, for instance 2 electrons, will repel each other. The effect is very similar to that exhibited between the poles of a magnet. The following example is in the accompanying workbook, Basic Units, Charge and Current. Part A is to find the number of electrons in 3 coulombs of charge. We know that 1 coulomb of charge is equal to 6.25 times 10 to the power 18 electrons. So, if we have 3 coulombs, the result will be 3 times that amount. So, 3 coulombs equals 3 times 6.25 times 10 to the power 18 electrons, which equals 18.8 times 10 to the power 18 electrons. Part B is to determine the number of coulombs of charge for a given number of electrons. By inspection, we can see we do not have enough electrons for even 1 coulomb of charge. So the question really becomes, how much of a coulomb do we have? This can be determined by dividing the given number of electrons by the number required for a coulomb. So, number of coulombs equals number of electrons divided by 6.25 times 10 to the power 18, which equals 9.38 times 10 to the power 16 divided by 6.25 times 10 to the power 18. Therefore, number of coulombs equals 15.0 times 10 to the power minus 3, or 15 millicoulombs. A battery may be considered to be a charge generator. The materials inside a battery interact to strip electrons from atoms and hold them at one end of a cell, while leaving the positively charged atoms at the other. This gives rise to a force between the cell terminals measured in volts. For a dry cell battery, this voltage is typically 1.5 volts, or if a few cells are connected together, this value can be doubled or trebled. If a voltage source is connected across a conductor, then the free electrons will start to flow. Current is defined as the rate of flow of charge past a point. That is, the number of packets of charge that flow past a point every second. The symbol associated with current is the letter uppercase I, and its unit is the ampere, abbreviated to the letter uppercase A. Current is represented on a circuit diagram by an arrow on a conductor indicating the direction of current flow. There is a relationship between current, charge, and time. The highlighted box shows current is equal to charge divided by time. Provided the charge is in coulombs and the time in seconds, then the calculated current will be in amperes. A current of 1 ampere is flowing if 1 coulomb of charge passes a point every second. The following example is in the accompanying workbook, Basic Units, Charge and Current. Part A is to calculate the current if 24 coulombs of charge pass a point in 8 seconds. We know that current I is equal to the amount of charge Q that flowed past a point divided by time t taken. In this case, charge was equal to 24 coulomb and time taken was 8 seconds. So, 24 divided by 8 gives a current of 3 amperes. Part B is to determine the number of coulombs that flowed past the point. We can use the same relationship as used in Part A. Substitute into the equation the value of 5 amperes for the current and 10 seconds for the time. Then, using algebra, we make Q the subject of the equation. So, 5 times 10 gives a charge of 50 coulomb. The definition of energy is the ability to do work, and it takes energy to cause an electron to separate from an atom. The symbol associated with energy is the letter uppercase W, and its unit is the joule, abbreviated to the letter uppercase J. Voltage is the measure of force between separated charges. The symbol associated with voltage is the letter uppercase V, and its unit is the volt, abbreviated to the letter uppercase V. A voltage source is represented in a circuit diagram by either of the two symbols shown. If the output voltage does not vary with time, termed a DC source, for instance a battery, it is depicted by two parallel lines where the longer line indicates the positive terminal. If the output from the source is time varying, termed an AC source, then it is shown as a circle with an inner symbol indicating the nature of the changing output. There is a relationship between voltage, energy, and charge. The highlighted box shows voltage is equal to the energy divided by the charge. Provided energy is measured in joules and charge in coulomb, then voltage calculated will be in volts. If it takes 1 joule of energy to separate 1 coulomb of charge, then the voltage between the charges is 1 volt. The following example is in the accompanying workbook, Basic Units, Energy, Voltage and Potential Arrows. To calculate the energy expended, if it takes a voltage of 12 volts to move a charge of 50 coulomb between 2 points. We know that voltage V is equal to the energy expended W divided by the amount of charge separated, Q. In this example, the voltage was 12 volts and the amount of charge moved was 50 coulomb. Then using algebra, we make W the subject of the equation. So 12 times 50 gives an expended energy of 600 joules. If a voltage source is connected across a conductor, then the electrons will start to drift from the negative to the positive terminal. This is termed electron flow. However, electron flow is a comparatively recent concept. Previously, a different concept of charge flow prevailed, termed current flow. Conventional current flow considers there is a flow of positive charge carriers from the positive to the negative terminal. Theory from now on will only consider conventional current flow. Voltage may be referred to in a number of different ways. Generally, the term voltage is used to describe the force that drives charge around an electrical circuit. When we speak of a battery having a voltage of 1.5 volts, this is being quite specific about the battery's capacity to drive charge. The term potential difference is used when considering the difference in energy levels between 2 points in a circuit caused by the presence of a voltage source. This is analogous to looking at the difference in pressure between 2 points in a pressurized water system. Finally, there is the term EMF or electromotive force, which is very much a historical term for voltage. Today, this term is generally only used when dealing with the output of electrical generators. However, these are all references to the electrical force voltage and are all measured in volts. The voltage or potential difference between 2 points in a circuit can be identified by an arrow or a reference term. If an arrow is used, it will always point to the most positive terminal. So in the first diagram, the arrow is pointing to the terminal A, and in the second, the arrow is pointing to the terminal Y. If the terminals are labelled, the labels can be used as suffixes to reference the voltage. The most positive terminal is always listed first. So in the first diagram, the voltage is termed V subscript AB, while in the second, the voltage is termed V subscript YX. The following example is in the accompanying workbook, basic units, energy, voltage, and potential arrows. In this example, we are required to draw on the potential arrows and identify the potential differences across each element with the appropriate subscripts. To start with, we only have the voltage across the terminals AD, termed V subscript AD. This tells us that the A terminal is more positive than the D terminal, so the potential arrow goes between the two terminals with the arrowhead pointing at the A terminal. From this information, and knowing that current always flows from the positive terminal to the negative terminal, we can sketch on the arrows showing the current direction. Now, taking each element in turn and recognizing that where the current enters the device is the most positive end, we can sketch on all the potential arrows and label the voltages. For element AB, the voltage is V subscript AB with the arrow pointing at the A. For element BC, the voltage is V subscript BC with the arrow pointing at the B. For element AC, the voltage is V subscript AC with the arrow pointing at the A. And for element CD, the voltage is V subscript CD with the arrow pointing at the C. Being able to accurately position the potential arrows and understanding the significance of the order of the voltage subscript notation is essential when using many of the electrical network theorems. Resistance is the term given to the ratio of the applied voltage to the resultant current flow in a body. A body is said to have a low resistance if a relatively small voltage results in a large current, and a high resistance if a large voltage results in a relatively small current. The symbol associated with the resistance is the letter uppercase R, and its unit is the ohm, abbreviated to the Greek letter omega. Resistance is represented in a circuit diagram by the symbol shown. There is a relationship between resistance, voltage, and current. The highlighted box shows resistance is equal to the voltage divided by the current. Provided the voltage is in volts and the current is in amperes, then the resistance calculated will be in ohms. This relationship is known as Ohm's law and is the basis of all the electrical network theorems. The following example is in the accompanying workbook, Basic Units, Resistance. To find the circuit resistance if a voltage of 28 volts causes a current of 4 amperes to flow. From Ohm's law, we know that resistance R is equal to the applied voltage V divided by the resultant current I. In this example, the applied voltage was 28 volts and the resultant current was 4 amperes. So, 28 divided by 4 gives a resistance of 7 ohms. It does not matter what part of an electrical network is examined, Ohm's law always holds true. Ohm's law enables that for any given situation where 2 of the 3 electrical factors are known, the third to be derived. Using the triangular representation of the law, if the voltage and the current are known, the resistance may be determined. If the current and the resistance are known, Then the voltage across the device may be determined. Finally, if the voltage across the device is known and its resistance, then the current flowing through the device may be calculated. Power is defined as the rate of doing work. The symbol associated with power is the letter uppercase P, and its unit is the watt, abbreviated to the letter uppercase W. Work is done or energy is expended when charge is moved through a potential difference. There is a relationship between power, energy, and time. The highlighted box shows power is equal to the energy expended divided by the time taken. Provided the energy is in joules and the time is in seconds, then the power will be calculated in watts. However, this relationship is not very useful in evaluating the performance of an electrical circuit, where we tend to be involved more with voltage, current, and resistance than energy and time. By using the previously discussed relationships, we know that energy can be re-expressed as voltage times charge. When this is substituted into the equation, it can be seen that charge divided by time can be replaced by current. Hence, power can be re-expressed as voltage times the current. Using Ohm's law and replacing the current term, this formula may be rewritten as power is equal to the voltage squared divided by resistance. If the voltage term is replaced, this formula may be rewritten as power is equal to the current squared times the resistance. The following example is in the accompanying workbook, Basic Units, Power. All three parts of this example require the power to be calculated. In Part A, we can use the formula power is equal to the applied voltage V times the current I. Substituting the values, voltage equal to 25 volts and current equal 2 amperes. So 25 times 2 gives a power consumption of 50 watts. In Part B, this time, we have to use the formula that contains both current and resistance. Power equals the current squared times the resistance. Substituting the values, current equals 4 amperes and resistance equals 20 ohms. So 4 squared times 20 equals 16 times 20, which gives a power consumption of 320 watts. In Part C, we need a formula that contains both voltage and resistance. Power equals the voltage squared divided by the resistance. Substituting the values, voltage equals 40 volts and resistance equals 2.5 ohms. So 40 squared divided by 2.5 equals 1600 divided by 2.5, which gives a power consumption of 640 watts. In general, an electrical circuit consists of a source and a load linked by an insulated conductor, where the conductor can be regarded as a pipeline along which electrical energy can be transported from an electrical source to a load, as illustrated in the diagram. The source is a supply of electrical energy, for instance, a battery, a generator, or a fuel cell. The load is a device that converts electrical energy into another form, for instance, heat from a fire, motion from a motor, light from a lamp, and sound from an amplifier. A conductor is a material with a low resistance and is made from elements that have many free electrons, for instance, gold, silver, copper, aluminium, and iron. An insulator is a material which has a high resistance and is made from elements that have few or no free electrons, for instance, glass, clay, rubber, PVC, and mica. One of the main difficulties electrical engineers experience is that it is impossible to tell what is happening in an electrical circuit simply by looking at it. Generally, the only way to determine the condition of an electrical circuit is through instrumentation, the most common of which is the digital multimeter, termed DMM. The DMM can measure both current and voltage for both alternating quantities AC and direct quantities DC. The DMM can also provide a readout of resistance. With this option, the meter acts as a DC source to feed the network with a known voltage. It then measures the current and calculates the circuit resistance using Ohm's law. The voltage and current options, either AC or DC, or resistance, are selectable by a switch. The connection to the network is made with two electrical probes generally colored red and black. The black probe is always connected to the COM socket, and the red probe connected to one of the other three sockets, depending on the function selected. Making a voltage measurement in a circuit is comparatively simple, as we are only looking to see the potential difference between 2 points. The DMM should be set to read DC voltage, and the probes located with the red in the V'-omega socket and the black in the COM socket. The probes can then be connected across the device as shown. In this case, the supply is 15 volts and the load has a resistance of 30 ohms. So the DMM should read 15 volts. This video clip demonstrates how a DMM is used to measure the voltage across a resistor. The probes are connected to the circuit and the DMM set to read DC voltage. Once the switch is closed, the DMM displays the DC voltage appearing across the load. Measuring current is not generally a simple process, as we have to redirect the flow of charge through the DMM. This means that the circuit under investigation has to be broken and reconnected through the meter. The DMM should be set to read DC current, and the probes located with the red in the A socket and the black in the COM socket. The probes can then be connected to the circuit as shown. In this case, the supply is 15 volts and the load has a resistance of 30 ohms. So the DMM should read 15 divided by 30, which equals 0.5 amperes, or 500 milliamperes. This video clip demonstrates how a DMM is used to measure the current flowing through a resistor. The circuit is broken and the probes are connected so that the current now flows through the DMM, which is set to read DC current. Once the switch is closed, the DMM displays the DC current flowing through the load.